Good morning, everyone. Thank you for attending today's webcast, Understanding Linear and Nonlinear FEA using Inventor and Nastran. Our presenter today is Keith Dorian, Solutions Engineer with Hagerman & Company. Before we get started, I wanted to let you know that you are in listening only mode. If you have any questions during the presentations, you may type them in the question panel on the right-hand side of your screen, and they will be addressed at the end of the presentation. As we close down the session today, you'll be prompted to fill out a survey, and we ask that you take a few moments to fill that out. Additionally, all registrants will receive a follow-up email containing a link for the recording of this presentation. And with that, I will hand things over to Keith.
Excellent, thank you. So the way that I kind of aptly named this presentation was Nature is Nonlinear, right? And the main goal of this is to try to validate design decisions before manufacturing or construction begins. And before I kind of start into the entire process, I did want to just make a couple of notes about the overall range of the simulation software that Autodesk has either acquired or developed over the last several years. And we've got a number of different tools depending on the real needs of the simulations that you're trying to accomplish. If you're trying to do any kind of fluid flow dynamic simulation, CFD is an amazing tool for that. Today the main focus will be inside of the mechanics side of upfront design in the Nastran In-CAD software. But there are also additional tools for dealing with composites or complex materials, as well as dealing with plastics and all of the manufacturing process involved with them. In the manufacturing side of, or in the mechanics side of the simulation, there are two tools, and again I mentioned we're using Nastran In-CAD, which is a CAD embedded tool set. So it gives us the ability to do advanced mechanical simulation right inside of our Inventor session. If we're looking for a little bit more robust and complete data set, then Simulation Mechanical would be a tool that you could use to further enhance the overall environment. So being able to do more complex assembly analysis or more complex interaction of components or a multi-physical type of simulation. And obviously with the Nastran In-CAD and the simulation mechanical space, you can use the Autodesk Nastran solver, which is a very high-level industry standard solution solver for both of these tool sets. So Nastran is a tool that sits inside of Inventor, and it can do a number of different types of simulations. In this case, we're just kind of looking at some of the more basic level scenarios, so just a linear static analysis to see how our parts might distort under standard loads, critical buckling analysis, so taking magnitudes of forces and seeing if it's going to cause a structural failure, finding different basic vibration information, in this case the normal modes of the harmonic frequency vibration values, what frequencies it would vibrate in nature, and then other tools like heat transfer, working with composite materials, dealing with more complex contacts, as well as doing some thermal stress. Beyond these, we can also do things like drop testings, heat transfer in a nonlinear transient state, doing dynamic response as well as nonlinear transient response, and then taking a number of these different scenarios and running multi-axial fatigue on those components. In this case, we're going to be working with the nonlinear statics portion of the software. And the concepts, or what we're going to try to cover today, is the main usage of linear analysis, some of the main differences between the two, how Nastran can help us look at and perform those nonlinear analyses, how to take existing simulations and convert them, and then review the changes in those results, and then obviously all of these things, how to take your designs farther. So what I wanted to do in this exercise, or in this this presentation, was I didn't want to throw a large, huge, complicated data set within this environment. So we're going to see some pretty basic simulations and just see some different ways that those some of these nonlinear type of scenarios may come into play. And the dominant reasons or the primary usage of linear analysis is, when you know the forces on the component are not going to change direction or they're not going to change magnitude. The other big aspect of linear analysis is when you have a static or a kind of a fused assembly, right? A weldment would be a prime example of this. Or if you're trying to work with just simulating one component within a larger design. As parts move and collide with one another, those contacts are going to change, and that in turn redistributes weight and force loads on those components. The other big aspect about linear analysis is we don't expect the model to deflect a huge amount, right? Usually like 1/20th of the longest dimension is really all we're expecting a deflection or less. And beyond that, if the deformation of that component, if it does start to get into some of those larger values, it's not contributing to the strength of that component. So some of the general assumptions, kind of as I was mentioning, the model doesn't move in a way that changes contacts, or they are already in contact with the components that they're going to be interacting with. Beyond that, the materials that we're dealing with, they're not going to pass beyond their material yield strength, so they're maintaining their linear function. They're not going to become plastic. And again, the last piece of this is the forces don't change direction or magnitude or distribution. So if a face starts to collapse on itself, that would change the overall total force load on that face. That in turn would be a nonlinear type of scenario. So a basic linear analysis, right? All of these, in this case, just a single rectangular beam, in this case mounted on the left side, simple 10 inches long, and it's got a 1,000-pound force on the far end. All of these values are easily calculatable, right? We don't need anything other than these equations to figure out what the total amount of deflection in this beam is going to be, as well as the total amount of stress applied to the base or the far left edge or face of this component. And so basically just kind of filling in the values, right? We've got 1 inch by 2 inch to get our total area. We can take the base and the height, divide that value by 12, get the moment of inertial point, and then use those moment of inertia and our length and the position of this component to define the overall deflection as well as the maximum bending stress. So nothing overly complicated inside of this space, just really just plugging in the numbers that we know using kind of tried and true equations to define these values. And the software can solve these exact same scenarios. So in my case, I've got just a beam that's 10 inches long, that's 2 inches thick. I'm going to jump into the Nastran environment. And in this scenario, I've already gone through the steps of setting all of this stuff up. Right? I've specified in this case a material that I want to use. It's just a generic material. There's no real settings in here as far as this component is concerned. I did make it match my PowerPoint to use the modulus elasticity as well as my Poisson's ratio. And if I jump into the material here, I can see those values. So my modulus elasticity and my Poisson's ratio. With those values in place, I've already defined the 1,000-pound load downward, negative 1,000 pounds. And I've grounded the far back end or fixed the back end. And from here I can solve. I don't need to worry about meshing it. I've already done that. The mesh in this case would have taken a very short amount of time. And in a few moments, we get that linear analysis. And from here, if I check the displacement, we can see that displacement matches what we're getting in our PowerPoint. So again, Nastran solves those basic equations in the linear scenario very, very quickly. Obviously in this case we're dealing with a very simple piece of geometry, but the workflow stays the same throughout any kind of geometry, right? One of the big advantages to Nastran In-CAD is that it can solve things with different types of meshing. So, in our scenario, I simply went in and said, make this a solid block of material, use a solid mesh. If this were, say, a very thin piece of material or a U-shaped piece that was very, very uniform throughout its shape, I could have used, say, a beam element and just simplified that mesh even farther. And that's one of those big advantages that we have using Nastran In-CAD versus using Inventor. Okay? So some of those things that we might need to interact with this beam that might affect the overall design of this, right? And the first one that I want to look at is just contact. So, in this case, we just kind of represented that this part was mounted to the wall, right, or mounted to a vertical surface, but how is it attached to that vertical surface? And in this scenario, I've built a channel piece that we've used to hold this component in place. And what ends up happening here is, in this scenario, as this part starts to deflect, the location of the end of the part, if you will, moves, right? So instead of being attached to this back left edge, it's going to slowly eventually come in contact with this bottom surface, and that in turn will change the overall output over the total displacement and the overall stresses on this component. And again, it's because of a contact across this face. So as soon as you start getting into that scenario where contacts are changing throughout a system, or contacts are originally not in contact and then they become in contact, a nonlinear scenario is becoming apparent. Right? And if I were to solve this using a linear analysis, those contacts would not update properly and we'd get just bad output. Usually what you end up seeing when you run this sort of a scenario is you get what we call clipping inside of this area, where essentially the two meshes overlap. Right? Now, obviously, they're supposed to come in contact with one another, so there's definitely something not working properly in that linear scenario. And if we have time at the end of the day, or the end of the presentation, I do have this data set that I can open it up and show what little minor changes needed to be made in order to make this function work. So contact is a definite proponent of a nonlinear scenario, and the big thing is, do the contact points change? And if the answer is yes, then a nonlinear scenario is the route you want to go. So the next aspect of this is follower forces, and what this means is essentially how do the forces on this component function within this object. So in this scenario that I just ran, the downward force that's being applied to that component is assumed to be a constant downward force. In this scenario, with a true follower force, that shape may change, or that direction of that force may change along the path of the deformation of our component. So, not only staying in contact with that face, but also, always pushing towards the direction of the normal of that face. And this is really, really important for specific applications. Obviously in this case, if it was some heavy mass that was pulling down on that component due to gravity, this isn't really all that applicable. But say, for example, I have a tank full of liquid, and I want to show the pressure on the outside or the inside of that tank, and use that information to see how the shape of the tank is going to distort. In that scenario, the forces are always going to push normal to the outside geometry, and as that geometry deforms, we need to make sure that the pressure is always maintaining that constant outward direction to our model. And in our case, we can see how this effect occurs in our environment. This will also give us a good chance to see how to take an existing linear analysis and simply change it to be a nonlinear analysis. So in our case, we're just going to see if having a follower force affects our model. So I'm going to switch back over to Inventor here. And I've got my follower force part file. And in my case, I'm going to switch over to my Nastran environment. And right now, I basically have the exact same configuration. I did make a minor adjustment here to this part. In the CAD model, I use the split tool so that I could specify a specific area for the force to be applied to. Nothing overly complicated, just making sure that I have a face, okay, split up. And if you've not seen that function before, I'll just jump over here real quick. All I did is I just created an offset work plane from the rightmost end of this part, and then I used the split command here to split this face into two separate faces. And the main reason you'd want to do that in the simulation environment is now I can apply specific forces to a specific area of this model. Okay? So back over to Nastran. So in this case, the first thing that I need to do in this simulation is I need to change my analysis type, because right now it is trying to run the linear static analysis. To change the analysis type, I simply right-click and choose Edit. And then in this case, I'll switch over to the nonlinear static type. From here, a number of options have changed, and one of the main pieces of the functionality here on the Options tab is I want to make sure that large displacements is turned on. And this is kind of a misnomer because large displacements doesn't necessarily mean this part's going to distort some drastic amount, right? In our case, we're getting some, 0.06 inches of material movement within the, a 10-inch component. So large displacement simply being on is what essentially enables the follower forces to be applied. So with this option turned on, follower forces will automatically take place. Okay. Once you've turned on the nonlinear functionality within the analysis, you will add into your subcases a nonlinear setup inside of that space. And so in this case, I'll go ahead and right-click on that and go to Edit. And basically what this is asking me for is how many times, based on the load or the simulation specified, does this system need to increment it. So in this case, if I do a 10, it's going to take the overall load, in this case 1,000 pounds downward, and it's going to break it up into 100, then 200, then 3, then 4, and so on and so on and so on. And it's going to compare those results, or not compare them, but stack those results into the system. So obviously the more increments I add, the longer the simulation will take, but potentially more accurate the results on this model. The intermediate output, with this option, what it allows me to do is control whether or not I get all of the increments and then be able to look through them. And in this scenario, because I do want to see whether or not this is truly affecting the analysis, I'm going to go ahead and turn that option on. If I didn't leave that on, all I would essentially get is the last increment as the solution. So I want to make sure to do that. So in this case, I want to go in and update my material. So we'll simply grab this and change our values here to match the materials that we want to work with inside of our component. Go back to my other page here to make sure I don't lose my numbers. I tried really hard to get rid of as many of these little steps as possible, so you don't watch me type in numbers. I know that's super boring to watch here, but some of these values do need to be defined. So we'll go ahead and specify our structural values. In this case, I know that I'm not going to exceed the yield strength in this component, and later on we'll start to look at changing the material properties to add the nonlinearity. If we leave this alone, we just essentially get a linear material, but a nonlinear force analysis. So in this case, we've updated our material. I'll go ahead and mesh this component real quick to do that. And then from here, I just need to add my constraints and loads. So let's go ahead and fix the back wall. And then we'll apply that downward load on this face. So in my case, I'm going to use a normal to surface load, select the location, and then in this case, a -1,000. Okay. So now that I've got my load and my constraint and my material and everything else set up that I need, I'll go ahead and run these results. So in this case, what we're seeing here is, as I mentioned, it's looking at each of those increments, in this case, the 10 increments that we defined, and it's doing all of the simulations within that increment. And eventually we'll get to that last 10th one and we'll get a full solve. All right. So in this case, I want to look at some of the results of this. To do that, I simply double-click on the results button. And then from here, I have the ability to change out what types of data I'm looking at. In this case, I want to see the total displacement. And right now, we're looking at the first increment, or a total load of a 10th, right? 10 increments, 0.1. And I can jump through to the last load and seeing here that my maximum loading is slightly less than what I had started with. Right? My original calculation showed the displacement on the end of this component at 0.66 or 0.066, and in this case we're now seeing a maximum value of 0.063. If I want to display that, I can simply hit display, and I can see that offset value. Some other things that I like to do inside of the Nastran environment, the first thing is I'll go into object visibility, and I like to turn off the mesh and the original undeformed edges just to get that stuff out of the way. In my case, I can see that downward force. It might also be helpful to take the loads out just to get your overall analysis just a little bit more cleaned up. Right? If I'm going to take screen grabs of this stuff, helps to kind of clear out some of that geometry. I can also animate from this space, so if I did want to animate this individual load, I can do that. One of the other neat tricks that you can do is if you run a multi-lodal or a multi-increment, if you right-click on here, you can specify to run a multi-set animation. And essentially what this would do is it would show me the maximum loading from point 1 of the load to a full 100%, so 10% up to 100. And the idea here is that I can see the part essentially distort based on that loading versus just animating from 0 to 100% in here. So there's a little bit of different settings there depending on what I want to see. Now the last piece of this puzzle is I want to find out whether or not the load that I applied is truly nonlinear, right? Did the follower force actually have a major effect on my component? And in this case, to check that value, all I have to do is go into my XY plot, and I can check this based on the maximum displacement versus the load scale factor. And as I grab this and load it, we can see in here that as the loading was set to 0.1 and as it ramped up through the different increments, we can see that we get a very, very close to a perfectly linear effect, right? And this is letting me know that in this scenario, I'm not exceeding any kind of material limitations. I'm not exceeding how this component functions within this space. And later on, I'll take a look at another simulation where we'll definitely get, different displacements based on the load, or a magnitude of displacement not linearly applied to the load. Okay? So the stress and the strain are not linearly function. And this is kind of important, right? Because sometimes we don't need a linear analysis, and this is telling us right away that we just went through the nonlinear function and the linear worked just fine, right? It would have output the same information. So the next kind of instance that you can look at a nonlinearity is the geometry itself. And there are scenarios where the component will change based on the amount of deflection in those components. And the example image that I've got in this picture here is is essentially a paper tray. And as that paper tray gets pulled downward, the overall shape starts to deflect and gives us some strength back. And another really common example would be like the bottom of a soda can. And the whole point of it is that as the pressure inside the can increases, the dome will essentially stiffen and become stronger to a point, and we can simulate that effect within the Nastran environment. Another example inside of a pressure vessel, right? The pressure is constantly normal to the faces. The shape of the tank may change, which will directly affect the stiffness of the tank shape. So in our case, we've got a quick model of this to kind of show. So what I've got here is just a couple of very basic models, and basically all I did here to kind of explain this model is I created the full shape of the tank, which in this case was a 48-inch tall 2-foot square. I then took that and cut out the data that I needed, and in this case I cut it at the middle of the component. So what I ended up with was essentially a fourth of the tank. Now the reason that I'm doing this is that I don't need to solve the entire tank to get the data that I'm after. In all reality, I can apply symmetry to this component and save myself the hassle of having to solve, essentially 4 times as much geometry or 4 times as much mesh data. I then again split this component at where the purple and the gray faces are to represent the water line within this tank. So with that in play, I can then specify where a pressure inside of the tank is being applied. Lastly, because I was dealing with a solid, I went in and deleted out all the faces I didn't need. So in this scenario, the 6 faces that make up a standard cube, right, I only really need 3 of those 6 faces. So I just deleted out the ones I didn't want. Now that step isn't required by any means, right? You can take very, very simple geometry and use it within this space. Beyond that, I could have potentially thickened this to the actual wall thickness, but in this scenario, it's a very thin-walled component, and trying to use the solid elements, right, a tetrahedral shape, to try to solve this might be very, very difficult. It would also take a long time to solve, because in order to get a mesh refined down that small, there would be tens of thousands or even millions of elements to make up this geometry. And instead, I can use a shell element to accomplish that same task. So in the environment, I've already done a lot of the setup in here, so you're not watching me do super boring mouse clicks and other values, but we will go through it. So the first thing that I defined is a shell element, and this shell element is this stainless steel material that I want to make this tank out of. And if I come in and take a look at the material, there's nothing in here out of the ordinary. In fact, all I did was went to select material and then use the Inventor material library to find my stainless steel material. Right. Had I set this up front before I jumped into the Nastran In-CAD environment, that material would have been available to me, and it would have already used these values. Okay. So in my case, I'll cancel that out. Back in here, where's our numbers? So it automatically populates these values for me with no interaction from me required. Secondly, I specified these solid elements to instead be a shell element. And to do this, all I had to do is just double click here, fast double click, and then specify what type of element they are. And Nastran can do 3 different kinds, right? Solid 3-dimensional elements, surface components, shell elements, and then if I'm doing things with like a frame structure, I can use linear elements to define these objects. So shell elements. With shells, I just specify how thick that material is. I then specified the faces that I wanted to work with, the bottom, and then the 2 walls of this component. Next, I had to go in and build up some of the rules about what I built. And the basic constraints in this case is I needed double symmetry, right? So I created the X symmetry, and there's really nice kind of macro buttons down here in the constraint dialog for that. So I just choose X symmetry, and then I chose my 3 edges that represented where the other half of this tank existed. I then repeated that exact same process for the Z symmetry on the left side of this component. And then finally, I grounded the bottom of the tank as if it were, sitting on the ground, so it can't move at all. Once I had that done, I needed to create the pressure load. And this did take a little bit of calculation up front to get these values essentially defined. I had to look at calculating the overall volume of the liquid that was inside the tank, and then use that value plus a couple of equations to tell me what the overall pressure was at the base of the tank. So going into the load here, we've got a couple of values that we need to define. And the first thing that we want to do is we selected the faces, in this case the 3 faces that were associated to the pressure, so the purple quote-unquote wetted faces. And then I just defined a negative pressure to make sure that it knew that it was pushing from the inside out as opposed to the outside in. Now in this case, I wanted to distribute the pressure in the way that fluid pressures are applied, greatest at the bottom and slowly decreasing to 0. So in order to do that, I jumped into advanced options. I specified that it's a variable load, and then I just picked these 2 corners, so here and there. And when I did that, it added those locations into the system, at which point I then specified at what scale did I want to apply that load. So in this case, 3.032 pounds per square inch at the bottom face of the selected faces, and then nothing at the top. So now that I have my pressure load defined, my model has already been meshed. As a general note here, if I go into mesh settings, I can change the element sizes. In this case, 3 inches is sufficient. I'll go ahead and regenerate this mesh and then resolve. Now, in this scenario, I did not change the simulation type. So in this case, we did just run a linear static analysis on this component. And if I check the displacement in here, we get some very random, kind of strange results. And essentially what's happening here is it takes that pressure that we've applied and it simply applies it constant, right? And the problem with this is that as the shape deforms, and in this case we're getting a very large amount of displacement in this model, that pressure is not updating given the shape of the new shape of this component. So we're getting some very strange results inside of this environment. And again, remember that we're only looking at essentially one edge of a 4-sided tank. So I want to compare these results against a nonlinear analysis of the same type. To do this, all I have to do is add a new analysis to this model. So in this case, I'm simply going to right-click and say New Analysis. I'll give this a new title, Non-Linear Pressure, and then change the type again. So in this case, another non-linear static. From here, it essentially duplicates that data. So we can see in here now I have my nonlinear static. If I want to rename the analysis, I can simply double-click on it just to keep track of what types of analyses I'm running inside of the space. So from here, I've got a couple things that I need to copy. Essentially, all of the data that I've created is the same. So all I'm going to do is simply drag them from the model portion of my browser into the analysis that I want them to be applied to. So in this case, I'm just going to grab our symmetry, our ground face, that pressure load that I had created, the pressure load, and then also my material. Oop, not idealizations. This. Come on. There we go. So there's our stainless steel component. So from here, I just need to remesh the model. Generate mesh. We can see that the size is a little off, so let's shrink this down to the correct size. There we go. And again, just like the last model I ran with the nonlinear analysis, you always want to go into the nonlinear setup, just to make sure that it's got the correct number of increments you want to run. Typically, I would probably, in this scenario with a pressure model, I'd probably increase this to 15 or 20. But for the sake of the simulation solve time, I'm going to leave it as 10. I do want to turn on the intermediate so I can see what the pressures look like at half the load and go from there. Let's go ahead and run this. So right away in this scenario, we can see that the overall shape of the distortion on this component is very, very different than the original linear analysis in this case. And once this completes, we'll be able to check that same deformation inside of this environment. So if I were to go to my results here, results, displacement at the final increment, and then display that. We can see here we have a very different shape and end shape of the model, as well as the displacement happening in a very different location on the component. And again, this is coming from the stiffening stress on this component as the pressure redistributes and moves around within the model. Beyond that, if I were to check things like our maximum displacement based on the load scale factor, we can see in here we are getting a nonlinear function, right? In the beginning, we have a little bump once the pressure starts to increase, and then as it gets to a certain point, it starts to essentially taper off. the amount of displacement. So we can see in this scenario that, one, the overall way that the pressure is being calculated is very different from the linear type to the nonlinear type. And then beyond that, the stiffening or strengthening of the part based on the shape deformation is being taken into consideration due to the incremental system in play here. And again, right, the way that the tank changes based on the pressure is just completely ignored in that linear analysis. So the last piece of this puzzle is the linear materials, or using a nonlinear material in the space. And in a linear environment, linear materials are essentially proportionate to the strain, right? And if we keep ramping up, if we keep ramping up the load, the stresses and deformations will simply proportionally change along with that value. So in my case, on that first analysis, we had a deflection of 0.067 inches at 1,000 pounds. If I were to multiply my load by a factor of 10, I'm going to get a deflection multiplied by a factor of 10. Realistically, though, that's not really realistic to our models themselves, right? Our components have a failure point, a yield strength where they're going to start to become plastic. And again, in this scenario here, you know, in a linear material state or in a linear analysis, they're only functioning inside of our plastic range of our stress strain curves for our materials, which is not realistic to the real world, right? Parts don't live in this space all the time, right? We start to exceed those strengths and we get some different functionality on those components on how they perform. And beyond that, we may not have a simple linear state on the a single Hooke's law space on our stress strain curve, right? This is pretty typical for metals, but we may have specific soft materials, for example, that don't function that way, right? And obviously, we have to go into the system and start to define those values. So there's different types of materials, different types of curves. Plastic, for example, has a Hooke's law section in the elastic stage, and then starts to become plastic after that specific yield point. Non-linear elastic, as we start to push and pull on those components, it has different compression strengths versus different tensile strengths. We get into hyperelastic components where they change their elastic states based on the loading. So in our case, I'm going to use our ABS component, and this is information that I pulled right from the Matweb website. If you've never been there, it's a fantastic website for finding physical properties of, you know, something like 75,000 different materials based on manufacturer, based on different processes on them. So there's, I think, 2,000 or 3,000 different steel alloys alone in their site. And all of the data that it came out with was using megapascals. And so I went through and tried to adjust these values to continue using our English units as we had been using. The system is intelligent to know the difference. So if I were to go in and start specifying, you know, 43 megapascals versus a PSI value, it would just make the translation. That was a new feature in 2017. It knows the conversion on its own. But in my case, I've already done all of that work ahead of time. So the orange line in this case is what I'm going to use for our model to define essentially how I want this plastic part to function. You know, I could go through as far as defining the true material curve, stress strain curve for this model. However, you know, that would take quite a bit more input, and for simplicity's sake, I'm just going to use our orange value. So at this point, let's break our model, right? We know some information about our original analysis. We're going to get a total stress of 29,000 psi, or about 200 megapascals. And we know that this ABS material will not be able to handle that load, right? It's just going to fail. And if I try to run an analysis with that level, it's actually going to get into the fracture phase of that material. So in this case, I'm going to halve the load and see if the part can withstand that. So in this case, again, I've got another Inventor part. Back to that same component we started with. Let's switch over to our Nastran environment. And all I'm going to do in this case is change our analysis. Nonlinear. Let me make sure that our large displacement is definitely turned on. And it should be by default, but always a good idea to check this. You know, given what we're about to do to this model, we're going to really rip it apart. So our material here, right now we're using a generic material. We can see that it's associated to that component. So in our case, we're just going to add a new material. And from here, I'm just going to go select our ABS or our acrylonitrile-butadiene styrene. It's located in our Autodesk material library, ABS. In this case, I don't need the G value, and I'll jump into our nonlinear scenario. In this case, this is a plastic component, so I'll go ahead and specify our plastic settings. And again, all I did is I'm going to use the I'm going to use some of the values from the Matweb website to fill in these values. In my case, let's go ahead and hit OK there. Some of these are a little bit off to what I want to use. 2488 E5, perfect. We'll set our value here to 0.34. Set our yield strength to 5584 psi. All right, so now we'll get into our nonlinear. So from here, I want to change our initial yield strength. And again, we've got some different values here that I want to use. So we'll just clear up these numbers. And then from here, this upper right portion of this table is essentially showing us our stress strain curve as points along the path, or key points along that path. And in this case, I'm just going to define the second value here to keep the material plateaued at the initial yield strength. So we'll define our value for the stress and then define 0.5. Then we'll define our strain value at that location. And if I go in and check the plot for this, I can see our stress versus strain plot inside of this space. So now that I've defined the linear material data for this component, the last thing I want to do is make sure we apply that load to this model. And in this case, I do want to apply it as a negative 500 or just a lesser value here. We'll generate our mesh. I think our constraint is already in place. We're good there. So again, and the way that I always use the Nastran space is, you know, if I forget a step, I always just go up top and check everything. So these are kind of broken down into the order of which you do them, usually, right? So the first thing I want to do is make sure my analysis is set up. So I just come up here and touch this and see, okay, well, I've got nonlinear static. Usually that means I need to come in here and check this. In our case, we've got the 10 increments, and we'll set this, turn it on. The next thing I want to do is make sure our materials are set up and our idealizations are set up. So I created a material, and in this case, right now it's using generic. So I'm going to grab our ABS, and I'm just going to apply that to the solid one. Now, in the model section, it shows us just everything that's available to us. And if we create multiple subcases or multiple analyses, all of the stuff that we've defined will show up in this model section, and then each analysis will then lay out what it's using. And in all reality, I could create a new solid material and call it ABS and then leave generic alone if I wanted to be able to swap back and forth. But given what we're trying to do here, I'm not all that deeply concerned about leaving the generic behind. In fact, I could just straight delete this since nothing is now using it. So I've got my material. We've got our idealization as a solid part. I've got my constraint and my load in place. I don't have any contacts because I'm dealing with a single part, so I don't need to worry about that. And then as far as my mesh control is set up, the size here is sufficient, so I'm just going to leave it alone, generate the mesh, and then run. And this is a huge differentiator than a lot of other software. I used to use ANSYS Workbench, this was some years ago, and the workflow to get from point A to point B as far as start to finish within the environment was very, very cumbersome. And you basically had to memorize every single step. And once you got those steps memorized, it was cake, but it's a lot of work to remember those, and then if you're only doing these once a month, to re-remember them when you come back into the software. Right? I go months at a time without using Nastran, and I can still pick it up and run with it because I know that if I start at the left and work my way across, I'm pretty much ready to rock. So in this case, let's run this. It's going to take a moment to solve this, and we'll see this part get really distorted. I need to put some hold music on while it's solving. Get myself some Nastran solver music. This won't take much longer. Another minute. Let's see if there are any questions. No, I don't see any questions yet. All right, so there's our solve. That took about 2 minutes to run. In this case, as I load those results, I have all 10 of the increments that I can tap into. And in my case, I just want to look at the displacement here. So we can see in here we're getting 200 millimeters of displacement. This is controlled by our units right now. So in my case, I was using CAD units, which this case was inches. I did change this. Honestly, I don't remember why. But it's using the modified SEI, which uses our linear values as millimeters. So we're seeing in here quite a bit of displacement. And if I display that, we'll see this part distorted to that value. Now right now it is giving us a kind of a representative of the deformation. If I jump over to our deform options, I can specify this to show me the actual deformation of this component, in which case, in this case, we can see that it's pretty much deformed to the point where it's obviously going to fail. Right? We knew that we were getting to the point of that excessive load, but one of the big things about using a nonlinear analysis and pulling all of the increments out of it is that we can use those to find essentially where some of that yield is starting to happen. So in this case, if I go into my XY plot here, we can see that we have a massive amount of displacement shift after about half of the load that we applied. So once we get to that 0.5 to 0.7 range, that's giving us kind of an idea of where that true value was. And in our reality, if I were trying to figure out where this component was going to yield under the load, I could do a couple of different things. Right? The first thing that I could do is change my analysis type to a nonlinear buckling. And with the buckling, I can then specify essentially what frequency to magnify my load. And then in this case, I would probably just apply like a 100-pound load as opposed to 1,000 or 500, and then say increment this by a factor of 1. Right? So it would just 1, 2, 3, 4, 5, and so on this component. And it knows all of its strength values from the material properties, and it would just go through the magnifications and try to find where that failure would occur. I could also set it to a much smaller value to try to get a more precise understanding of where a buckling event was going to occur on this component. But the big thing here that we're seeing via the displacement versus load scale is that at some point the load is exceeding what this component can yield, and it drops off, giving us a large amount of deformation in this component. So in this case, we knew we were going to exceed the limitations of the part, but we can see that within the results. And again, beyond that, we can see the nonlinear effects within the XY plot, within the deformation versus scale. So in conclusion, in linear analysis, don't discredit it. It has very high potential for simulating some real-world environments, but it's very easy to step into a nonlinear environment based on a number of factors, right? How are the forces being applied to this component? Is it coming in contact with other models? What types of materials am I using, and do they have low yield points that I'm probably going to start stepping into? And then lastly, how do the forces on my component apply to this model? Is it a pressure load? Is it a force that's going to change over time? Right? And in those sort of things we can effectively solve for in a nonlinear analysis. And remember, nature is nonlinear. So with that, just find out if we have any questions. Let's take a look at the panel here. SN curves. So I believe SN curves are referring to for fatigue analysis. And yes, absolutely. So we would definitely want to switch the material type to or switch the solution or the simulation type, the analysis type, to a fatigue analysis. And just to kind of take a look at that here inside of the environment, the first thing we would do is change the analysis type. And one of our types within this space is our fatigue. And then beyond that, just click there. We'll just do fatigue. And then beyond that, the material itself has a fatigue SN curve that we can build. So you have the SN data or the EN data depending on what pieces of information you know about the component, what type of material you're dealing with. How do I make this section bigger? I can't see my chat questions. There we go. I've only used linear static simulator and Inventor, which you need to input the number of iterations and check convergence before you determine the validity of the study. I noticed that some of the steps in the nonlinear analysis were iterating 20 to 30 times. Does the step simply not end until you reach some predetermined convergence data? Yes, so Nastran is doing some of that work on its own in the background. There are some additional configuration settings inside of the simulation here. Where is the button for it? It's in, oh, I'm in a fatigue. That's why I'm not seeing what I want. Edit. Nonlinear static. And then we go into here, and we can get into the advanced settings and then specify all the rules about how we want to define convergence and whether or not we want it to terminate based on bad data output. And absolutely, right? When we did that last analysis in this case where we really distorted the part a long ways, it ran the simulation something close to 38 or 40 times before it finally determined a convergent set of data. So absolutely, you can specify those settings up front.
I don't think that there's any more questions, so this will conclude our broadcast. If you have any additional questions, simply reply to the confirmation or reminder email you received from GoToWebinar, and we can route those to the appropriate parties to get those questions answered. Once again, if you can take a few moments to answer the short survey, we would appreciate it. It will automatically appear when you close down the session. Thank you for attending today's webcast, and have a great day.